probably you can explain the examiner with this graph. All right. Fine then. Okay. So let's go ahead. Okay. So today I'm going to discuss about the connection of resistances, okay, in series as well as in parallel. Okay, so let me set the topic for the day. Okay. Basic circuit arrangements. Okay. All right. Now, first let me write some expressions for power, energy, etc., etc. Okay. So power, okay, in DC circuits, power can be given as P is equal to V into I. Okay, this is for DC circuits. Okay, on the other hand, in case of AC circuits, power is always Vrms into Irms into cos phi. Okay, what is phi? Phi is the angle between voltage and current. Okay, do not worry about it. Let me discuss in detail when I handle single phase AC circuits. Okay, this is for AC circuits. Okay. Now, at this point of time, let us consider only the DC circuits. So power P is equal to, okay, using Ohm's law, you can either substitute an expression for voltage in terms of resistance, or you can substitute an expression for current in terms of resistance. Okay. Say for example, let me keep voltage as it is, and in place of current, let me write I is equal to V by R. Okay. So that gives me power expression as V square divided by R. Okay. What we have done is we have substituted I as V by R. Okay. So this is your first expression for power. This is your second expression for power. Okay. Now, likewise, I can also substitute, say for example, V is equal to I into R. Okay. So in the original power equation, that is P is equal to V into I, let's substitute V as I into R. So what do I get? I get IR into I, or P is equal to I square into R. Okay. So these are the three different expressions for power, which is pretty useful when you handle the numericals. Okay. So that is about the power. And next we have, the energy. Energy. So where do we come across this term called energy? Okay, so this energy term comes into picture in every billing cycle of your electricity consumption, right? In every month, okay, maybe probably end of the month, the state electric board person, okay, who is also known as meter reader, he will visit your house or flat, and he will issue the bill. Okay, so that bill is nothing but, okay, it is consisting of the details about the power consumption over a period of time. So energy is nothing but, okay, power consumed over a period of time. So energy is given by P into T. So it is the power consumption over a period of time. So for, let me give you a physical example. As I said, electricity bill, if you take that as the example, electricity bill, which consists of the energy consumption for a month. So basically, the time factor in case of your electricity consumption, or in case of your electricity bill, is 30 days. Over a period of 30 days, how much energy you have consumed. That's your electricity bill. Okay, so E is equal to P into T. Okay, and SI unit is, watt second. Okay, or joules also you can say. Okay, that is your SI unit. Okay, on the other hand, in normal day-to-day light, we also use commercial unit. Okay, commercial unit of electricity. Okay, so the commercial unit of electricity is kilowatt hour, kWh we would say. Okay, kWh. So 1 kWh is known as 1 unit of energy consumption. Okay, energy consumption. That means to say, if your electricity bill, city bill has a reading of, let's say, 270 units. Okay, so in your electricity bill, if you just take one electricity bill and if you inspect closely, there will be something like 270 units, 100 units, etc. That means to say you have consumed 270 kilowatt hours of energy. Okay, because 1 unit is 1 kilowatt hour. So 270 units is 270 kilowatt hour. So that is how we correlate the commercial unit of electricity with the SI unit of electricity. Okay, so that's the commercial unit of electricity and the standard SI units of electricity. Okay, so this can also be asked in Y1. Okay, they may ask you that what is the unit of, what is the commercial unit of electricity? Okay, it is kilowatt hour. Fine. So that's about the energy. Okay, any doubts in this? Or known stuff only? I'm just repeating it. Okay, we are just recalling the basic definitions. All right, so now let us come to the exact topic. Okay, so let me consider now series connection of resistance. Series connection of resistance, all fundamental equations. This you have already studied in your previous class. Okay, even then, even in basic electrical engineering, there can be some questions related to series connection of resistances as well as parallel connection of resistances. Normally they'll ask this type of questions for 6 marks. Okay, now series connection of resistances. Okay, let us get into this. Consider that we have 3 resistors. Okay. For the sake of simplicity, I have taken only 3 resistors connected in series. All right. Now, across this series combination, a DC source having a potential V volts is connected. Okay. And the resistance values be R1, R2, and R3 respectively. Okay. Let I be the current which is flowing through the circuit. Right? Now, in case of series circuit, the observation is that the current remains the same. Okay, why the current remains the same? The current remains the same because the current doesn't have any diverting paths, right? The current is having only one path. So when the current travels in one particular path, the magnitude of the current remains the same in the circuit. So in case of series connection of resistances, the very important observation is that as the current is not having any diversion paths, current remains the same. Current remains the same in the sense, if you connect an ammeter, okay, if you connect an ammeter, okay, if you want me to show you, let me show you. Let us say I will connect an ammeter. This is just for your understanding purpose. Okay, a DC ammeter is connected. Okay, the polarity should be reversed. Or else ammeter needle will kick back. This side. So this ammeter will read the current flowing through the circuit. Okay, if you place the ammeter next to R1 or next to R2 or next to R3, doesn't make any difference. Okay, wherever may be the position of the ammeter keeps reading the same current. So current remains the same in case of series resistance. Okay, on the other hand, when this current flows through R1, okay, it gives a voltage drop of I into R1. Similarly, when this current flows through R2, okay, it gives a voltage drop of I into R2. So that means to say the voltage across resistances can vary. Can vary. Okay, I'm just writing this can vary because what if you select equal resistances? Okay, if you select the equal value, the voltage drop remains the same. Okay, but nevertheless, in our explanation, we have taken R1, R2, and R3. They are what you say unequal resistances. So voltage across the resistance can vary. Okay, now let us mark the voltage. Okay, when the current I flows through R1, okay, the corresponding voltage, let us mark it as V1. Okay, similarly, when the current I flows through R2, the terminal voltage that appears across R2, let's take it as V2. All right. Similarly, when I flows through R3, the terminal voltage, let us consider it as V3. Okay. All right. Then we can write V1 is equal to, by Ohm's law, I into R. Similarly, V2 is equal to I into R2 and V3 is equal to I into R3. R3. Okay. But we can observe that the total battery potential V is equal to the summation of individual potentials, right? The individual voltage drops across the resistances. So V is basically V1 plus V2 plus V3. Algebraic sum. Because in DC circuit, there is no angle coming into picture between voltage and current. So the addition of currents or addition of voltages always going to be the algebraic sum. Okay. All right. So therefore, V is equal to V1. What is V1? IR1 plus IR2 plus IR3. Since in a series circuit, current is remaining the same, you can take out I outside the bracket. So you are left with I times R1 plus R2 plus R3. Okay. Or you can write V is equal to I into some R equivalent, where R equivalent is R1 plus R2 plus R3. Okay. So whenever the resistors are connected in series, the total resistance or the equivalent resistance going to be the sum of the individual resistances. Okay. All right. So this is the expression for series connected resistances. We have already studied. Okay. So next up we have the parallel connection of resistances. Say for example, we have three resistors connected in parallel. Say R1, say R2, and R3. Okay, they are connected in parallel. R1, R2, R3. And the whole combination is connected across a battery. Okay, let's assume that the battery is having a potential of V volts. Okay, now the circuit is closed, right? So there will be a flow of current. Okay, let I be the source current. Okay, where source is nothing but the battery over here. Okay, now though I haven't given um, an explanation to KCL and KVL, since you have already studied KCL and KVL, you will be able to understand the current diversion as well, right? So what happens is that the source current, goes in this direction, and at this particular node, you can see that the main current I is experiencing several diversion paths, right? So for this main current, okay, at this particular node, say node K, okay, there are three diverting paths. So what will happen is the current gets diverted, okay, in the form of I1 and say I2 and say I3 respectively. Okay, so the main current comes over here. Okay, at node K, the main current is going to split into three components, I1, I2, and I3 respectively. All right. Now, at this particular node, the three currents will, meet at this particular node, and it will come out as again I. Okay. So this is what happens in case of parallel circuit. So in case of parallel circuit, okay, note or observation is that I varies. I varies. Okay. Since I gets diversion path, I gets diversion path to flow. Okay. On the other hand, if you look at the potential, okay, now this potential is V, right? The battery potential is V. Now, the same battery potential, okay, if you look closely, okay, the battery is actually connected right across R1 as well as R2 as well as R3. That means to say, see, each end of R1, R2, and R3 is connected together, and that common node is given to the positive terminal of the battery. Similarly, the other remaining ends of R1, R2, and R3 is being connected together, and that junction is connected to negative terminal of the battery. So in this process, okay, what is happening is each of these resistances are receiving the same voltage. So in case of parallel circuit, voltage across the resistances, remains the same. Okay, so this is the observation between, or you could also say that the differences between series and parallel circuit. Okay, so let us write at node K, okay, we can write I is equal to summation I1, I2, and I3. Again, it's an algebraic sum. Okay, on the other hand, where what is I1? By Ohm's law, you can say that current is voltage by resistance, right? What is the voltage? The applied voltage. What is the resistance? R1. Similarly, you can write I2 as V by R2, so on and so forth. I3 is equal to V by R3. Okay, let's substitute the current values in the main equation. So we have I is equal to I1. So I1 is V by R1 plus I2. What is I2? V by R2 plus I3 is V by R3. Okay, and you can see that voltage is common. So let's keep the voltage term outside the bracket. So we would get 1 by R1 plus 1 by R2 plus 1 by R3. Okay. Or we can write I is equal to V into 1 by R equivalent. This can also be written as V by R equivalent. Okay, just to show you the terms which are sitting within the parenthesis, I have written in this particular format. So I is basically V divided by R equivalent, where your 1 by R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3. Okay. So this is how we reduce basically the parallel combination. When multiple resistors are connected in parallel, you can use this particular formula. Okay. Um, for example, if R1 and R2 are connected in parallel, okay, you would have written 1 by R equivalent as 1 by R1 plus 1 by R2, okay, which is basically R1, R2, okay, and that is R1 plus R2. And if you take out the reciprocal, okay, you would get R equivalent, which is R1 into R2 divided by R1 plus R2. Okay, so this is for the two resistances connected in parallel. On the other hand, if R1 is equal to R2 is equal to R, okay, you would have obtained R equivalent as R into R divided by R plus R, that is R square divided by 2R, okay, or it is R divided by 2. Okay, it would have been half of the individual resistance value. Okay. So these are the simple special cases. Okay, so this is the reduction formula for parallel connected resistances. Okay, any doubts in this?
Sir, I have a general doubt. Why doesn't current decrease on passing through a resistor?
Hmm.
Like it remains the same.
Which one in series?
No, both in series and parallel. Like when, for example, in parallel connection, when a current I2 passes through a resistor R2, still it remains I2 only. It doesn't decrease.
No,
Resistance, nothing but.
okay. See, decrease in the sense what you know. See, this particular part of the circuit, it offers some amount of opposition R2. Okay, based on that opposition, magnitude of I2 will flow through it. Okay, in every path, it is experiencing the opposition. Okay, and that opposition we have assumed it as R1, R2, and R3. Accordingly, the current distribution takes place. Okay, so I1, I2, and I3, it is unequal. Okay, because the resistances R1, R2, and R3 are different.
Sure, but despite the opposition, first the current I flows through it, and
Hmm.
after passing to R1, R2, and R3, still the current I flows through it. It didn't decrease. It's the same
Okay.
current, even
Ah,
after opposition is offered.
yeah, it's the same current. It's something like what you think about the what do you say piping mechanism. Okay, let's say I have a main pipe here, okay, and I will divert, okay, the water which is coming into the main pipe, okay, into three different paths. Okay, say path 1, path 2, and path 3. Let's say this is the diameter is D1, this diameter is D2, and this diameter is D3. Okay, so based on the diameter, some amount of water will flow through this, some amount of water will flow through this, some amount of water will flow through this. In the end, if I were to provide a junction somewhere over here by connecting W1 here, W2 here, and W3 here, and if I provide an outlet, okay, let's say this is my outlet. Okay, the water what I have supplied from this end, the same water will come out of this end. Okay, now, which pipe is getting more water, which pipe is getting less water, depends on the diameter. Okay, so you cannot just destroy the amount of water what you have circulated. Okay, what you have circulated, you will get it in the end. Okay, it cannot just vanish in the pipes, okay, except for external disturbances such as leakage, etc., etc. Okay, so similarly, this is one physical phenomenon. Similarly, in case of circuits also, okay, you know, basically this follows the principle of conservation of charge. You cannot accumulate at a point. Okay, the charge should flow through. So the charge basically flows through, let's say, the top path, bottom path, and the middle path. Okay, but at the outlet, if you were to add up all these charges, you will again end up in getting Q. Okay, so the distribution of current I1, I2, and I3 takes place based on the resistances of the path. Okay, even then, when you let's say observe the output current, okay, you connect one more ammeter somewhere over here. When you observe how much current I am getting at the exit end, okay, uh, you will come to know that the exit end current will be the same current what is being sent from the positive terminal of the battery. Okay, the diversion takes place, but there will be a junction at which all the diverting currents are collected back and again circulated into the circuit. Okay,
Okay, sir. So what exactly happens in a resistor, sir? For example, in a series current, there's just one path, but
okay.
still the current remains same. So what are we achieving by adding a resistor?
Which one? Okay, okay. What are we achieving? You are saying, right? Okay, I'll tell you. Let's say I have my source here. Okay, and let's say I have my load over here. Okay, I'm considering the load as incandescent bulb. Okay, just I'm giving you a resistive circuit example. Let's say this incandescent bulb, okay, is made up of a good maker. Let's say Philips. Okay, same rating, 60 watt. Just imagine that it is 60 watt operating at 220 volts of electricity. Okay, now the load, okay, and the source is connected using wires. Okay, now let us say, for example, we have used a good grade wire, good grade wire, which is providing an ohmic value of 2 amperes. Let's say this is 220 volts, and let's say the resistance of the lamp, let us say it is about um, say 50 ohms. Okay, so this is my case 1 scenario. Okay, let us say in case 2 scenario, the same source and load I'm going to consider. The same load I'm considering, so the ohmic value going to be 50 and the source value going to be 220 volt. But in the second case, what I've done is, instead of considering a good wire, let's say this is V-Guard wire, V-Guard brand wire, I've considered some local made wire, okay, which doesn't have any quality rating or ISI standard. Okay, and let's say this wire resistance is about 20 ohm, 20 ohm. Okay, now you assess the two situations here. Okay, same source, same load, but the transmitting medium, okay, I have what do you say changed. In case 1, I have gone for a good transmitting medium which is having lower resistance value, and I'm taking a high resistance value. Both basically follows a series circuit convention, right? But due to the change in the value of resistance, what happens is that the current drawn by the first circuit, let us call it as I1. Okay, I1 is equal to um, you can say V by R, right? So V divided by R equivalent. So 50 plus 2, this is going to be 52. So it is 220 divided by 52 ohms. Okay. It's about 4.23 amperes of current. Okay. On the other hand, in the second case, if you look at, okay, I2, so I2 will be again 220 divided by 70, it is 70. So 220 divided by 70. So that's about 3.14 amperes of current. Okay. Now whatever what the general example whatever I had given here, okay, say R1, say R2, say R3, okay, all these R1, R2, R3 are related to these scenarios, okay. So don't consider that the R1 or R2 or R3 is just a junk value what we are taking, okay. So all these resistance values are existing in one or the other way, okay. The example what I have given over here, okay. So in every house the resistance varies, okay, depending upon the type of transport media or what you choose, okay. The second level of understanding would be calculating the voltage which is present across uh, the lamps, okay. You know that if the resistance is more, the voltage drop across will also be more. So what happens is that if you choose a higher um, resistance value, okay, or rather if you choose a wire which is having higher resistance value, okay, what will happen is most of the voltage gets lost across the transmitting wire itself, okay. So 220 you are supplying, okay, and some part of 220 is going to appear across, let's say, 20 ohm resistor, okay. The remaining voltage which is 220 minus Vx will appear across your lamp, okay. On the other hand, when you use a wire having 2 ohms of resistance, okay, let's say this is my resistance, the voltage which is coming across, let's say 2 ohm is some Vy, all right, and the voltage which is coming across this particular bulb is 220 minus Vy, right, the leftover potential. But remember one thing, your Vx is greater than Vy, simply because the resistance in second case is greater than the first case resistance, okay. Due to which, let us say this is load voltage 1, and let us say this is load voltage 2. Due to which what happens is that in the first case, load voltage is higher. On the other hand, in the second case, load voltage is lower. Okay, that means to say, in the first case, lamp glows with higher intensity. On the other hand, in the second case, lamp glows with lower intensity. Okay, so this is the implication of the change in the value of resistance. Okay, is it understood?
Yes, sir. I got it. More the volt resistance, more the loss in voltage.
Yes, you will end up in wasting the energy across the resistance terminals, but actual load what you are using is receiving lesser voltage value. Okay, if the operating voltage is lesser, obviously you will not be able to extract the good amount of work from the appliance. So that is the implication, and that's the reason you must have seen in your homes as well. The moment there is voltage dip, okay, immediately your fans, okay, starts to run at a lower speed, and your lamps starts to give the light at a lower intensity level, right?
Yes, sir.
Yeah, so that's the thing. Now, the problem with the syllabus is that, I mean, if you ask, I can give you some physical examples. If you can't, I cannot get into much of physical examples because of the time limit also. Okay, so no worries. If you have any doubts, you can discuss in the class. Okay, if I know, I can tell you right away. If I don't know, I can always go back and I can study and come. Okay, hope I have cleared your doubt.
Yes, sir. I got it, sir.
Yeah,
Thanks.
good. Thank you. Okay, so today we have discussed about series connected resistances and parallel connected resistances. All right. So in the next class, let us also discuss about two circuit rules, okay, which are called as the current division rule as well as voltage division rule. Okay. So in the next class, let us study about those rules. Okay, and we can also solve some simple DC circuits problems as well. Okay. I hope you have entered your attendance in the required format. Okay. If you have already given the attendance, you don't have to give again. Okay. Fine then. I will stop my today's lesson. Tomorrow let's meet up. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.